Hey guys, Professor Calculus is here, and today in this video I'm here with solving this integral for you. Before we go, make sure to like and subscribe as it is free and you can always change your mind later. So, the trick that we've used before to solve the integrals like this was that we could raise the whole thing to the e to the ln of that thing. So we just change the form of it and we'd still have the same result. And for example, in here, I can move this coefficient here, which means that my integral is going to become 0 to 1 of e to the root x ln of root x dx. And I can move this radical out of here, which means that I'm going to have the integral from 0 to 1 of e to the half root x ln x dx. Now, here I'm going to utilize and use the series of e to the x. I'm going to write it in this color. E to the x, the series for that is the infinite sum from 0 to infinity of x to the n over n factorial. And if I put e to the half root x ln x to the power of n, I'm going to be getting the infinite sum from 0 to infinity of half root x ln x to the power of n over n factorial, which means that it's actually going to be the infinite sum from 0 to infinity of half to the n times x to the n over 2 1 to the nx over n factorial. Now, I'm gonna now replace this expression right here. Therefore, my I is going to be the integral from 0 to 1 of the infinite sum from 0 to infinity of half to the n x to the n over 2 ln to the n x over n factorial dx. And I'm gonna take this n out, this sum, infinite sum out. It's gonna be the infinite sum from 0 to infinity of, I'm gonna take this 1 over n out as well because it's a constant, 1 over n, and I'm gonna take this one out as well. So it's gonna be half to the n over n factorial, the integral from 0 to 1 of x to the n over 2 ln to the n x dx. Now, here I'm gonna introduce a new variable. I'm gonna use a substitution here. I'm gonna say t equals to negative ln x. Therefore, x equals e to the negative t, and dt dx is negative e to the negative t dt. And if x equals 0, t equals to infinity, and when x equals to 1, t equals to 0. Okay, now I can do this replacement here. That's my integral. It's going to be the infinite sum from 0 to infinity of half to the n over n factorial, the integral from 0 to 1 of. So my x here is e to the negative t n. It's going to be e to the negative t n over 2. And it's negative t over 2. I'm going to replace negative t to the ln x here, negative t to the n. And for dx, I'm going to replace negative e to the negative t dt. Notice that how this negative sign here can change the bounds of my integral, and I forgot to change the bounds here. It's actually going to be infinity to 0, and this integral sign is going to get absorbed into this integral, and it's going to make my integral to change and reverse the bounds. So the bounds are going to flip, and I'm going to have the integral from 0 to infinity of e to the negative t n over 2 negative t to the n e to the negative t dt, and it's going to be equal to the infinite sum from 0 to infinity of half to the n over n factorial the integral from 0 to infinity of e to the negative t n over 2 minus t negative t to the n dt. So it's going to be the infinite sum from 0 to infinity of the series here, half to the n over n factorial the integral from 0 to infinity of e to the negative, I can factor it out, negative t times n over 2 plus 1 times, I can expand this 2 out as well, it's going to be negative 1 to the n or t to the n dt, and I can move this negative 1 out, and it's going to be the infinite sum from n to infinity of negative 1 to the n half to the n over n factorial the integral from 0 to infinity of e to the negative t times n over 2 plus 1 t to the n dt. And I can absorb these two together. Thus, I'm going to be able to write this as the infinite sum from 0 to infinity of negative half to the n over n factorial the integral from 0 to infinity of e to the negative t times n over 2 plus 1 t to the n dt. Now, I'm going to do another substitution here. I'm going to say u equals t times n over 2 plus 1. My bounds are going to remain the same because infinity is multiplied by a constant, and constants in limits of infinity ain't got no value. And thus my t is going to be u over n over 2 plus 1. And my du is going to be dt times n over 2 plus 1. Thus my dt is going to be du over n over 2 plus 1. And therefore, my integral is going to be the infinite sum from 0 to infinity of negative half to the n over n factorial the integral from 0 to infinity e to the negative u, and t equals to this thing here, u over n over 2 plus 1 to the n, and dt is this one here. So it's going to be du over n over 2 plus 1. And my I is going to be the infinite sum from 0 to infinity of this whole boring thing here, the integral from 0 to infinity of e to the negative u to the n over 2 plus 1 to the n times du over n over 2 plus 1 to the n. Thus I equals the infinite sum from 0 to infinity of negative half to the n over n factorial, the infinite sum from 0 to infinity, so this is supposed to be 1, of e to the negative u to the n du over n over 2 plus 1 to the n plus 1. And I can move this thing outward here. thus my I is going to be, again, this boring infinite sum from 0 to infinity here. And multiplied by my integral from 0 to infinity e to the negative u to the n du. Now, this integral here is defined as pi function, which is exactly equal to n factorial. And this thing and this n factorial here would cancel out, and I'm gonna be having my integral to be the infinite sum from n equals 0 to infinity of negative half to the n over 2 plus 1 to the n plus 1. Therefore, the integral from 0 to 1 of root x to the root x dx is the infinite sum from 0 to infinity of negative half to the n over 2 plus 1 to the n plus 1. And that is the final answer of our integral right here. Thank you for watching this video. If you enjoyed, please like and subscribe and share my videos, and I'll see you next video.